Hello everyone from Math 2000, Linear Algebra. It's Professor Wenson here again with a video on your Zybooks section 6.5. It's titled Rank and Nullity. Now you've already heard me use these words, I just never wrote them down in the section 6.4 video. The rank is the dimension of the column space of a matrix, which we'll also see is equivalent to the dimension of the row space. All right, and the nullity is the dimension of the null space of a matrix. Right? And we saw how to find the column space and the null space of a matrix in the video on section 6.4. All right, so let's get into the section. All right, again, you got the opening here, some objectives. All right. So the rank of a matrix. The rank of an m by n matrix A, denoted by rank of A, is the number of linearly independent column vectors in an echelon form of A. So echelon form or reduced echelon form. So basically the number of pivot columns. Because remember, all the pivot columns correspond to a set of independent vectors, independent column vectors. So since the number of linearly independent columns of A is equal to the number of pivot columns in an echelon form of A, Gaussian or Gauss-Jordan elimination should be performed to find the rank of A. Alright, so I'm just going to read through some of these because you've seen me put a matrix into reduced echelon form plenty, either on the calculator or by hand with, elementary row operations. So their example here is, here's a 3 by 2 matrix, and they put it into reduced echelon form for us, and we notice, there's a pivot in the first column, a pivot in the second column, so these columns of A, negative 217 and 213, those column vectors are independent. So matrix A has two independent column vectors, therefore the rank of matrix A is 2. It's that simple. Alright, so then you're asked to do the same for these. I'll leave these to you. You can enter this is a 3 by 6, enter that in your calculator. This is a 4 by 4. You know what, I'll do this first one. I'm going to put this in my calculator and come back when I have it in reduced echelon form, and we'll find the rank very, very quickly. I'll pop the calculator up once I have that. Okay, so my calculator should have just popped up on your screen, and I've put this 3 by 6 matrix into reduced row echelon form, and we're seeing these leading ones. The first column, the second column, and the fourth column have these pivot entries. So the rank of matrix A, the number of pivot columns in reduced echelon form is 3. So I enter 3, check. Wonderful, that is correct. Very, very simple to identify the rank of a matrix. And you do the same for this 4 by 4. Alright, so how about this? True or false? The rank of an m by n matrix is less than or equal to the minimum value of m and n. Alright, like back up, just think about it. Alright, think about it. The number of pivot columns, say you have 3 pivot columns, everywhere there's a pivot entry, that pivot is in a column and a row. So the number of pivot columns will be the same as the number of pivot rows. So the number of pivots you have can't be greater than the smallest number of rows or columns. So this is a true statement. The rank of a matrix is going to be less than or equal to the smaller number of the row number or the column number. This is a true statement. It can't be any bigger than the smaller of the two. The rank of the n by n identity matrix is equal to n, yes. Right? All n columns would be pivot columns. The rank of the zero matrix is equal to 0, yes. Remember, a zero matrix is just a matrix where every single entry is a 0. So no pivots at all, no leading ones in any row or column. So this is also true. Okay. So just a few more things to know about the rank of a matrix. Alright, now again, I just showed you it's pretty easy to find the rank of a matrix using echelon form or reduced echelon form and just counting the pivots. This way they describe here of finding the rank using determinants. I'll show you one example, but this is definitely not the preferred method in my opinion. So here, the rank of a matrix A can also be computed using determinants. So by the invertible matrix theorem, right, if the determinant of A is non-zero, then all columns of A are linearly independent. This result also applies to a minor of order K of matrix A and can be used to determine which columns of A are linearly independent. Right. So for instance, a minor of order K of a matrix A is the determinant of a K by K submatrix of A. So the rank of an m by n matrix A is equal to the maximal order of a non-zero minor of A. Alright, so let me show you what the whole, now they talk about this, they describe the process here. Let me show you with this example. Alright. So we're given this matrix A, it's a 3 by 2 matrix, right? And that means that the rank of A is going to be less than or equal to 2, right? Which is the smaller, right? That's the minimum value of the row numbers and column numbers, right? So the rank cannot be 3, right? The rank can either be 2, 1, or 0. All right. So then we start, now again, this is this alternate method, find the rank of A using these determinants, these minors. So I'll start with the minors of order 2. And we'll start with this maximal number here and see if we can find any non-zero minors of order 2. Now remember, they said a second ago, a minor of order K is the determinant of a K by K submatrix. Because remember, you can only find determinants of square matrices, right? This is not a square matrix. But there are submatrices, matrices that are part of this matrix within it that are square. Now, if it's a 3 by 2, in order to make a 2 by 2 matrix, I would need to get rid of a row. So let's say I got rid of the first row. Now I'll cover it with a marker. There is a 2 by 2 submatrix. So I'll take the determinant of this 2 by 2 submatrix. And this is 3 minus 7. This would be negative 4. And hey, this is non-zero. And if the determinant is non-zero, that means that these two columns, 1, 7, 1, 3, are independent. So it really wouldn't matter if the two other components I covered up are, because the 1, 7, and 1, 3, you can't do anything to 1, 7 and make it look like 1, 3. That's what we're saying here. So if these two are independent, then these two columns here are independent. The rank must be 2. All right, so this is, again, non-zero determinant for a minor of order 2. And if we're finding a non-zero determinant for a minor of a certain order, and that's the largest possible order, that means that the rank of the matrix is 2. Now, if this ended up being 0, then I would look at some other submatrices. There's another 2 by 2 submatrix, but its determinant would also be non-zero. So again, you'd see that the rank was 2. But if that didn't work, I'd get rid of the third row, and you got another 2 by 2 submatrix. Its determinant would be -4 as well, non-zero. So we're seeing here that the rank is 2. All right. Now, if none of those worked, then I'd go down to order 1, where I get rid of a row. Well, I'd have to get rid of 2 rows and 1 column, right, to make 1 by 1s. I'd have to get rid of 2 rows and 1 column. So say I got rid of these 2 rows and the second column. There's a, that -2 that you're seeing. That's a 1 by 1 submatrix, and its determinant would be -2. So that's not 0, and but we found some minors of order 2 with a non-zero determinant. So this matrix has a rank of 2. All right, it's the one that's with the largest order. All right. Let me show you an example here. All right. So for this one, and they're doing the same thing. They're saying, what is the maximal order of a minor? Well, it's a 3 by 4. So I mean, you can't make a 4 by 4 matrix out of this. The largest submatrix you could get would be order 3, would be a 3 by 3, which again is the smaller of the two, row number or column number. A has 3 linearly independent columns. Well, I don't know yet. All right, I don't know yet. But in order to make this into a 3 by 3 submatrix, you'd have to get rid of a column. So if I got rid of the first column, say I got rid of the 197, then find the determinant of this 3 by 3, and that's going to be going back a ways. You can use a calculator. Remember, there were lots of methods. Use cofactor expansion, or there was that special way you could do a 3 by 3 where you copy the first 2 columns again and then do all those cross products. But find the determinant of that 3 by 3, and if it's non-zero, then it's rank 3. But if that equals 0, then you get rid of the second column and try that 3 by 3. If that's equal to 0, get rid of the third column. Try that 3 by 3 determinant. And if that's equal to 0, try getting rid of the fourth column. Try that 3 by 3. Now, if all the 3 by 3 submatrices have a determinant of 0, then you make 2 by 2 submatrices, which you'd have to get rid of 1 row and 2 columns. So say I got rid of the first row and the last 2 columns, or the first row and the second and third column, first row, second and fourth column, whatever. And there'd be a lot of those. All right. But again, you could also very quickly just put it in reduced echelon form and count the number of pivots. And if it has 3 pivots, then it's going to have 3 independent columns. So again, I'll leave these last 2 to you. All right. Now the relationship between the rank, the row space, and the column space. Now we saw column space and row space in section 6.4. What we're going to see here is that the rank is the dimension of the column space, which is also equivalent to the dimension of the row space. As I kind of said that earlier, right? Remember, every pivot, all those leading ones, all those pivot positions are, they're in a row and a column. So the number of pivot rows is exactly the same as the number of pivot columns. So the rank is not only the dimension of the column space, but it is also the dimension of the row space, right? Which they're kind of getting to down here, right? So the dimension of the column space of a matrix is equal to the dimension of the row space. Additionally, the dimension of the or the rank of the rank of one matrix is equal to the rank of its transpose, right? Because if you just transpose, you're still going to have the same pivots. Right? The pivots wouldn't change, the number of pivots anyway, if you just write the transpose. So the rank of a matrix is equal to the rank of its transpose. The dimension of the column space is equal to the dimension of the row space, and again, those are the rank. Right. All right. So for example here, let A be a matrix with a rank of 4. So would the rank of A transpose also be 4? Yes, right? The rank of a matrix and its transpose will be the same. The dimension of the row space of A is 5? No. Right, the rank is the dimension of the column space, or the dimension of the row space, same thing. They'll be the same number. So this would be false. And remember, the dimension of a space tells you how many vectors will be in a basis for that space, right? So a basis for the column space of the matrix would have 4 vectors, yes. If the rank is 4, that means the dimension of the column space would be 4, and a basis for the column space would have 4 vectors in it. All right. Okay, so reading through this, they're telling you that, again, the relationship between rank and the existence of a solution to a system, A times X equals B. So if A is some m by n matrix and B is an m component column vector, then the following statements are equivalent. Now that you've seen this before, what it means for statements to be equivalent means that if one is true, all of them are true, and if one is false, all of them are false. So AX equals B has a solution would be true when this is true, when B is in the column space of A. Remember talking about the column space last section. And the rank of A, if these are true, then this will be true. The rank of A will be the same as the rank of the augmented matrix. All right, again, if these are true, this will be true. And if one of these is false, all 3 will be false. So let's read through this example. So say this is our matrix A, 3 by 3. This is some column vector B with -5, 2, and C. They make an augmented matrix with A on one side, B on the other. They put it in reduced row echelon form for us. And then they say, if C equals 16, would -5, 2, 16, would B be in the column space of A? Well, let's see. Look at the reduced echelon form. If C was 16, this last row would be 0, 0, 0, 0, which is fine. You have 0 equals 0. And then this system would have infinitely many solutions, right? There's a free variable. So there would be a solution to the system AX equals B, meaning that B would be in the column space of A. You could write -5, 2, and 16 as a linear combination of the columns of A. Now, is the rank of A the augmented matrix there, A with B, and the rank of A, are they equal for any value of C? Well, no. What if C were 17? Then there'd be a 1 here, and there'd be a third pivot. This would have a rank of 3, whereas A would have a rank of 2. So if C is not 16, right? If C is not 16, the rank of the augmented matrix will be 1 more than the rank of A, right? And that ties into this, because if C is not 16, well, then that system has no solution, and if it has no solution, then these other things are false as well. So this would be false. It's only good for when C is 16. All right. Next part. So we've talked about the rank of a matrix, right? That's the dimension of the column space or the dimension of the row space, same thing. Now let's talk about the nullity of a matrix. Now, we talked about the null space in section 6.4, or the kernel of a matrix in section 6.4. This is just the dimension of that space. Right? The nullity of a matrix A is the dimension of the null space of A. And I did point this out in the last video in section 6.4, that when you put matrix A into, reduced echelon form, the number of free variables, the number of non-pivot columns, columns without pivots, ended up corresponding to the dimension of the null space. You saw that in a couple examples again last video. So it's real easy to find rank and nullity together. To find the rank and nullity of a matrix, put that matrix into echelon form or reduced echelon form. I prefer that. The number of pivot columns is the rank of the matrix, the dimension of the column space, the dimension of the row space. The number of non-pivot columns, which you see them highlighting here in red or pink, is going to correspond to the number of free variables if you were solving a times x equals 0, right, to find those vectors that belong to the null space. And those number of free variables, those number of non-pivot columns of A, is going to be the dimension of the null space. That'll be your nullity. So the rank of A, the number of pivot columns in reduced echelon form, the nullity of A, the number of non-pivot columns in reduced echelon form. That simple. And if that's the case for all matrices, then we get the rank nullity theorem says that the rank of A plus the nullity of A will be equal to the number of columns of A. Notice it's an m by n matrix, and this is n over here, the number of columns. They're stating that up here in this activity. If you play the animation, you can see it too. But this right here is the rank nullity theorem. That for any m by n matrix, the rank of the matrix plus the nullity of the matrix will be equal to the number of columns of that matrix. So here, for example, suppose A is a 4 by 9 matrix. If the nullity of A is 6, right, so the dimension of the null space is 6, there's 6 free variables, what would be the rank of A? Well, it'd have to be 3, wouldn't it? It would have to be 3. Because 6 plus 3 is 9, the number of columns. So you're seeing that here. Now the next question is, can the nullity of A be 3? And the answer to that would be no. As remember, we talked about a little bit about rank earlier. If this is a 4 by 9 matrix, the highest the rank could be would be 4. Right. Also, if the nullity of A was 3, then the rank would have to be 6. But we just said the rank can't be higher than 4, right? The smaller of these two numbers. So the nullity cannot be 3. And they explain all that down here. Hopefully that made sense. All right. Now finally here, this is you're going to get used to this later as well. Especially we're going to talk about a section much later, probably not till chapter 9, but there's a nice relationship between these four fundamental subspaces of a matrix. Now remember the column, if it's an m by n matrix, remember the column space of the matrix is a subset or a subspace of Rm, right? The first number of rows. Remember the null space was a subspace of Rn. And then if you look at the transpose, right, that would be an n by m matrix. And remember the column space of the transpose was the same as the row space of the original matrix. So the row space of the matrix would be a subspace of Rn. And the null space of the transpose, which is called the left null space of the original, right, of A, would be a subspace of Rm. And if the column space has dimension k, then the left null space will have a dimension m minus k. And the null space has a dimension n minus k. And again, this is coming from the rank nullity theorem. All right, remember, if the rank is k and there's n columns, then the nullity has to be n minus k. And then if you look at the transpose, right, that would be an n by m. So the transpose would have m columns. So if the rank is k, right, the dimension of the row space, then the null space of the transpose, right, or the left null space of A would have m minus k as its dimension. So these all go hand in hand with this rank nullity theorem. Again, last section, I'm hoping you've seen the videos on section 6.4 because I'm not going to go that much into this anymore. And then here's a little picture again. Again, both these spaces are in Rn. Both these subspaces would be in Rm if A were an m by m matrix. Again, we're going to talk a lot more about this later. We're also going to talk about the fact that these spaces, the column space of A and the left null space of A, and the row space of A and the null space of A, these pairs of spaces are actually orthogonal spaces, but we're going to, we're going to talk about that a lot later. All right. So, for instance, if A was a 3 by 5 matrix, what is the maximum value for the rank of A? I've already talked about this. It'd be 3, right? The rank can't be higher than the lower of the two numbers. So the largest value the rank could be would be 3. And when rank is largest, nullity is smallest. So if the rank were 3, the nullity would have to be 2. Remember, the rank plus nullity needs to be equal to the number of columns. So the smallest value for the nullity would be 2. If the largest value for the rank is 3. Oh, I forgot to check that one, but of course it's right. All right, and then you have a challenge activity. We'll do a couple of these. What's the rank and nullity? No, this is just a 0 matrix. There are no pivots, so the rank is 0. And remember, the rank plus the nullity is the number of columns. So there are 3 columns here, 0 plus 3. Right, no pivot columns, right? None of them are pivot columns, and all 3 of them are non-pivot columns. Yeah. Now here, maybe you see it, maybe you don't, but it's a 2 by 2. Now you can put it in reduced echelon form, but I'm seeing right now, there's only 2 vectors here, only 2 columns, and these columns are independent. Remember, if there's only 2 vectors and you want to know if they're independent, they're independent if they're not scalar multiples of each other. So this has 2 independent columns. If you were to put this in reduced echelon form, it would have 2 pivot columns. It would be just the identity matrix. So rank 2 and then, nullity 0. Because again, the rank plus nullity should be the number of columns. Now they also did with the determinant, right? If the determinant is non-zero, that means all the column vectors are independent. another one. Now this one is already written in reduced echelon form. There are 2 pivot columns, so rank is 2. There are 3 non-pivot columns, so if you were doing that solving that a times x equals the 0 vector, trying to figure out what vectors x belong to the null space, there are 3 free variables, dimension 3, right? So the nullity would be 3. And again, the rank plus nullity should be the number of columns, and it should be pretty simple for all of these. Let's look at the last. I'll look at the last level, see what it gets. I think it asks for the rank and nullity all the time. Okay, this is a little different, but not much harder than this activity here. What is the maximum and minimum values? What's the maximum nullity of A? What's the minimum nullity of A? Those should be pretty easy to figure out. All right, and finally, remember this has been mentioned before, but now we're just adding more statements onto it with the word rank and nullity. Remember this invertible matrix theorem? So it's restated now to include more results. Right now, the following statements are equivalent. If A is a square matrix, right, n by n. So if you have a square matrix, the following statements are equivalent. Meaning, again, if one of these is true, all 9 of them will be true. And if one of these is false, all 9 of them will be false. So A times x equals 0 has only the trivial solution. If that's true, that means that A is row equivalent to the identity matrix, and A would be non-singular or invertible. That's what non-singular means. It means invertible. If it's invertible, that means the determinant's not 0. And if any of these are the case, that means that both the row and column vectors of A are linearly independent, right? All n rows would be independent, all n columns would be independent. So the row vectors would form a basis for Rn, so would the column vectors. And if all n columns or all n rows are independent, that means the rank of A is n, and the rank plus nullity needs to be the number of columns, and if the rank is n, the nullity would be 0. Right, and the null space would only have the 0 vector, only the trivial 0 vector in it. Alright, so one last activity here, right? If A is invertible, then the rank of A is 0. No, the rank would be n. If it's an n by n matrix and it's invertible. If A is an n by n matrix, if the nullity of A is 2, then A is not invertible. Well, yeah, because if the nullity of A is 2, then 9 is false. So then the invertible statement would be false as well, right? So that's a true statement is not invertible if the nullity is 2. And then you have your additional exercises, right? Again, I'm not, some of these are on your assignment, some are not. I would still recommend looking at all of them. Get more practice, more exposure to the material, get better at it. And of course, you can always look at the solutions, but please try to work these out. Try to figure things out before you look at the solutions. Right? If you're just copying solutions down, you're not going to learn anything. And if you have any questions, of course, send them my way in the Canvas inbox, or however you can contact me. Send me a message, and I'll get back to you as soon as I can. And thank you very much for watching.